Okay, today we are going to be talking about molecular structure and geometry. So, we've learned how to do Lewis structures, but we're going to get into the molecular structure, showing the actual geometry. So, Lewis structures represent that arrangement of the valence shell electrons in the molecule. They allow us to see what bonds with what. So you get to see a single bond here, a double bond there. You get to see what's going on, where everything is. But with the molecular structure, you not only see all of that, but you see the geometry. The Lewis structure is going to show all those lone pair electrons as extra dots. When you get into the molecular structure, depending on how you represent it, you could see them, you could not. Okay, so we are going to talk about, with regards to shape and geometry, we're going to talk about VSEPR theory. So VSEPR theory is the valence shell electron pair repulsion theory. And so we can break that down. Basically, those electron pairs in that valence shell are going to repel each other. So really now it just comes down to, well, what do we define an electron pair as? And so not only would an electron pair be those extra electrons, the lone pair electrons, but it would also be a pair of electrons that's in a bond. And so when we talk about our valence shell electron pair, we're going to talk about electron regions. So if we had in an electron in this region here, if we had something like water, H2O, and we look at it and we say, well, on water you have two hydrogens bound to an oxygen, and then two sides have a lone pair. If we wanted to know, right, there would be four electron regions, one up top, one right there. So let's count and go ahead. One electron region there, one electron region there, one electron region there, and one electron region there. Four total electron regions. Okay. Now, if you had something like carbon dioxide, which is a carbon double bonded to an oxygen, even though each of these oxygens has two bonds, they're only going to count as one electron region. So this would be one electron region, this would be one electron region for two total electron regions. All right? And so when you count them, you're talking about that centered atom. It's the geometry off of the center. So, off this oxygen, how many regions are there? Well, 1, 2, 3, and 4. There's 4 regions. Off this carbon, how many regions are there? Well, there's 1, 2. So those would be the electron regions. And then depending on electron regions, you're going to get a shape. So let's take a look. Okay, and this shape is, again, is caused by the electron pair, or those electron regions, repelling each other, pushing each other away. Those regions want to get as far apart as possible from each other. Okay, so that's where we say that the repulsion causes molecules to form specific shapes. All right, those things are going to push apart because all of them, whether they're a lone pair or an atom, have electrons on the outside, which are going to repel each other. The negatives are going to repel each other. So this causes shapes. All right. So when we look at this chart here, this figure, it's going to show us what shapes we have. Now, how we look at this is the first thing we need to see is electron regions. How many regions are there? okay? And so with our carbon dioxide, that's CO2, we were talking about having the two regions, right? We had a carbon double bonded to an oxygen on that side, that was one region, and double bonded to an oxygen on this. And so what you would see here with the two regions, okay, with us having two regions, right? One right here and one right here. Two regions, we're looking right here, two electron regions. It is linear. That is going to be its shape. So if we wanted to know what shape carbon dioxide is, it would be linear. Because since it has two regions trying to get as far apart as possible, they're going to be on opposite sides of that center. And that's going to give us that angle, 180 degrees, which we know from geometry is a straight line. Okay, then let's take a look at that water that we were looking at. So with water, on the other hand, we had the oxygen in the center with 1, 2, 3, 4 regions, right? And so if we're going to do 4 regions with oxygen, again, 1, 2, 3, and 4, we're going to find that it is a tetrahedral. All right, the shape there is a tetrahedral, in which case, in 3 dimensions, 4 things are getting as far apart as possible. And that gives us this, somewhat a pyramid shape on the outside, with that central atom being right in the middle. Okay, but we have to go one step further with this chart because this is not a tetrahedral. What we look at now is how many positions, okay, how many of those electron regions are occupied by a lone pair. And so when we talk about that, well, there's a lone pair right here, right? This is a lone pair, non-bonding, and this is a lone pair. So we don't have one region with lone pairs, we have two regions with lone pair, meaning it is bent, okay? So the geometry for water would be bent. All right. And since two things are bent, we're going to say bent tetrahedral. So that I know you understand that it is that tetrahedral shape because the angle will be different. This is 109.5. Bent on trigonal planar is 120 degrees. All right. And that's really, guys, VSEPR theory. It's not crazy. It's just that these things are going to repel each other, and because they repel each other, we're going to get a very specific pattern. We are not going to get too much into the 5 or 6 region figures, but you should know from 4 regions, the tetrahedral down. I don't think linear will be a hard one to understand, so really it's learning, 2 different geometries with a few variations.